Okay, so welcome to lecture number 15, and today we will continue from the last lecture. We were talking about magma and this game rock paper scissors. In the last lecture, we saw how this game forms an algebraic structure called magma because it satisfied closure property, right? And then we began talking about a new property of algebraic structure, and it's called commutativity, right? Commutative property. And we saw commutative means A and some operation O B must be equal to B, same operation A, right? For example, if you take any operation plus addition, so 2 plus 3 and 3 plus 2, right? They are same. So plus this symbol addition satisfies commutative property. But 2 minus 3 and 3 minus 2, they are not equal. So negative, this minus sign, this subtraction does not satisfy commutative property, right? What about multiplication? Well, 5 times 6 and 6 times 5, they are same, 30 and 30. So multiplication satisfies commutative property. What about division? Well, 1 by 2, not 1 by 2, 2 by 3, it means 2 divided by 3 and 3 divided by 2. Are they equal? Well, not. It is not. Because another is 1 point something, right? And the next is greater than, it's like half. 3 by 2 is half, but 2 by 3 is different, 1.0 something, right? Less than half. So addition and multiplication satisfies commutative property, but subtraction and division does not satisfy commutative property. Now we saw this game, this rock paper scissors, it satisfied closure property, so it was a magma. But then we started to see in the table that across the diagonal, the principal diagonal, the opposite elements were equal, right? So that kind of scene in table, when it appears, it is proved that it satisfies commutative property. So this game satisfies commutative property too. First, it satisfies closure property, and the second, it satisfies commutative property. So it is not magma, it is a commutative magma. That's why I said it is a special kind of magma. Now let's see how does it satisfies commutative property. I want to show you, give you a picture through this game. So let's begin. I think we should do on the paper. So yes. Now for commutative property, we know A operate B must be equal to B operate A, right? So let's say R operate S. What is the answer? Well, among rock and scissor, the winner is scissor. Now let's do the opposite. SOR. Who wins? Well, scissor operate on rock. The answer is scissor. Oh shit. I made a mistake. Among rock and scissor, rock is gonna win. Scissor and rock is gonna win, right? So we saw this and this are equal because both produces R. So ROS equal to SOR equal to R. So it is commutative. We can check for another element. Let's say POS, SOP. Are they equal? Well, POS, paper and scissor, the winner is scissor. Scissor and paper, winner is scissor. So they are equal. It means they are equal. Now let's check another combination. Let's say ROP, right? So what is ROP? Rock operate paper and paper operate rock. Who wins? Well, the winner is paper here because rock and paper winner is paper. Paper and rock winner is paper. So they are equal. So it means this game not only satisfies closure property, it also satisfies commutative property. So what is this? So now it is called commutative magma. So what is the commutative magma? an algebraic structure, let's say a set and some operation such that this operation is defined from this set A cross A to A, right, where this operation satisfies following axioms. So for commutative magma, it should satisfy closure, and second axiom is commutative. If a structure satisfies these both, it's called commutative magma. If it only satisfies closure, then it is called magma, right? Now we have to say this a magma is a very weak algebraic structure. A very weak algebraic structure, you see. In most of the engineering, we try to design a strong algebraic structure so that we can work, right? And we will see some examples. So we need a stronger algebraic structure, not only magma, because magma only makes sure that after operation your element belongs to that set, right? It doesn't say more about how about combining many elements together. What happens then? It doesn't say about such things, right? Commutative extend further, it becomes stronger, because commutative closure only says operate two element, you get in the set. Commutative says, well, no matter how you operate, either first operate on second or second operate on first, you get the same element will be in the set. So it gives more power, right? It gives more power. Now what if, suppose, so we have magma, it satisfies closure. Now there is one axiom, this is first axiom. If it satisfies any algebraic structure, if satisfies closure, it becomes magma. Now what if it satisfies associativity? Associativity says first combine two element and then operate with third element, or combine the first two element and then operate the third element, the answer will be same. It's a very powerful structure. It says combine second and third element first and then combine with first element, or combine first and second element first and then combine with third element, the answer should be same. If this is same, then it is called associativity. Example could be, let's say R of A is 2, B is 3, C is 4. Now let's say our operation is plus. So what is the answer of this? Well, 2 plus, first we have to calculate whatever is in the bracket. So 3 plus 4, 7. 2 plus 7 is 14. Now check this part. So A is 2, O is plus, B is 3, and then O is plus, C is 4. Now 2 plus 3 is 5 plus 4. Oh, here I made a mistake. 2 plus 7 is not 14, it is 9. So 5 plus 4 is 9. So they are equal. It means this symbol plus satisfies associativity. What about subtraction? We keep same number. 2, 3, 4. Here also 2, 3, 4. Our operation is minus. So minus. What is the answer? Well, 2 minus 3 minus are they equal or not? That's what we are checking. So 3 minus 4 is minus 1. Answer is 2. Minus plus 1. 2 plus 1 is 3. So we got 3. For this part we got 3. Now for this part, 2 minus 3 is 1. 1 minus 4. 1 minus 4 is minus 3. So here we got 3 and here we got minus 3, and they are not equal. So not equal, it means subtraction symbol. This minus subtraction does not satisfy its closure property. What about multiplication? Well, let's see. We have to check A operate B or C equal to A operate B operate C. We choose the same number 2, 3, 4, or we can choose any number we want, right? So let's say -1 operate 2 operate -2, let's say -2, multiplication 3 dot -2, right? That's so what is the answer? Well, -2 multiplied 3 multiplied -2 is -6. Answer is 12. Now let's check for this part. What happens? A is -2, B is operation is multiplication, B is 3, operation is multiplication, C is -2, so -2. So -2 times 3 is -6, and -6 multiplied with -2 is 12. So they are equal. It means multiplication is associativity, right? What about division? Well, let's check here. So we have to check A operate B operate C is equal to A operate B operate C, right? Let's choose a number. A equal to, let's say, 2. This is division, right? So 2 divide, and let's say B is 4, division is this, C is 6 divide, right? So what is the answer? Well, 2 divide 4 divide 6. What is 4 divide 6? 4 divide 6 is 2 divide 3, right? And 2 divide 3 is what? Well, it is 2, and we have to do the reciprocal of it. So 2 into 3 by 2, which is 2 cancel, the answer is 3, right? Now let's check for this part. So A is 2, operation is division, B is 4, so you have to put 4, operation is division, C is 6. So what is the answer? Well, 2 divide 4 is 1 by 2, 1 by 2 divides 6. So what is the answer? Well, 1 by 2 divides 6 is equal to 1 by 2, and we have to do the reciprocal of this. So it is 1 by 6, to answer is 1 by 12. So we see it is 3 and it is 1 by 12. So it does not satisfy. Division does not satisfy associativity. So what we saw, why are we doing all this? Because we are doing all this because I want to make you understand what is associativity is, and if our game rock paper scissors satisfies this property. But before that, we have to see what associativity is, right? So now the next is, so what we saw, plus, now this plus and multiplication, this symbol is and. You can write and. I am just putting it because it's easier to write. So plus and satisfies commutative, we saw it, and associativity. But subtraction and division does not satisfy commutativity and associativity. C for commutative, A for associative, right? Now let's check our game, rock paper scissors. Well, so we have set rock paper scissors. Now to check commutativity, A operate B operate C must be equal to A operate B operate C. Now let's choose ABC. So we have only 3 elements. So this will be rock, let's say this is paper, this is scissor, and this is A is again rock, operate, B is again paper, operate, C is again scissor, right? We can choose any in order, right? So this rock operate, paper operate, scissor, the answer is scissor. Rock operate paper, is answer is paper, paper operate scissor. So what is rock operate scissor? Well, rock operate scissor is rock. What is paper operate scissor? Paper operate scissor is scissor, but R is not equal to us. So we got contradiction. R equal to us? No, R does not equal to S. So it does not equal to, does not equal to, does not equal to. It means our game does not satisfy commutative property. And we can check in any order. Let's say if we put A is this, so A operate, A is P now, B is, let's say, R operate, C is our only one option, that is S. So now is it equal to P O R operate S? Well, let's check. So P operate, rock operate scissor, answer is rock, rock wins. P operate rock, paper wins. Operate scissor. This one is here. So what is POR? POR paper wins. POS S wins. They are not equal. So it means our game is not associative, right? It does not satisfy associativity property. Let's check another example. Let's say scissor operate paper operate rock. Is it equal to scissor operate paper operate rock? Well, let's check. So scissor operate. So answer is scissor operate. First we have to calculate this one. So paper operate rock is what? Well, paper. Scissor operate paper is what? Scissor. And this is operate rock. Now scissor operate paper is what? Scissor. And scissor operate rock is what? Rock. So they are not equal. So no matter how you choose ABC, you are never going to find any single combination where it will satisfy associativity. Not a single. And associativity is not about only satisfying associative for only one element. No. For only one set of combination. No. It should satisfy for every combination. Right? Every combination at all. Among all these set. Whatever number it is, we have how many here it is? 1, 2, 3. So you have to satisfy associativity in all the combination of this. Not only one. But here it is not even one. In every case it fails. So it is not associative. Right? So our game is not associative. But plus was associative. It was commutative. Our game was only commutative and closure. Right? Multiplication was commutative and associative. Minus and division failed both. And so our operation. It also failed. But it didn't fail commutative. Right? Subtraction and division fails commutative too. But our game didn't. Our game satisfied commutative, but it failed associativity, and it also satisfied closure. Right? Now, let's say, so what we have for now, we said we studied three property, which is three axioms. So what are our axioms of a simple algebraic structure of this form, S, some operation. So if our algebraic structure is of this form, S, star, let me write it here. Let A, star be an AS, which means algebraic structure, where the operation star is defined from A cross, again cross I am saying, this is Cartesian product, right? So A Cartesian A to A, right? Such that star satisfies following properties. What are the properties? First, it should satisfy closure. If this satisfies closure, we get what? Magma. We read this. If it satisfies closure and commutativity, we get what? Commutative magma, right? Now the third, third we got associativity, right? Did it satisfy associativity? Well, it did not, right? It did not satisfy. So, is there any structure where this associativity can be satisfied? That is our question, right? So, let's see. Let's consider a algebraic structure n, plus, right? And what is plus? Plus is the Cartesian product between these two set on same set and producing an element in the same set. Is it closed? Well, what is n? The set is 1, 2, 3, so on. It is set of natural number, right? Or maybe I should stop here, right? First you should digest this one, what's happening here, and in the next video we'll try to study this structure. So thank you for this.